Good morning, students. Today we learn meter bridge experiment. The first experiment is to calculate the specific resistance of the given wire. We have chosen a manganese wire. The temperature coefficient of this wire is very low, so there is less resistance change with the increase in temperature. So the wire has nearly same resistance. So that's why we have taken it. Okay. So this is the circuit diagram of the experiment. So this is the meter bridge. It has got 100 centimeter wire, and over here we have the two gap for the connection of the resistance. In the left gap we connect the unknown resistance wire. In the right gap we connect the resistance box, from which we can calculate the resistances, and using a galvanometer we'll find out the null deflection point over here. Okay, so I'll just introduce this component. This is our meter bridge and this is the resistance box from which I'll take out the unknown resistances, and this is your galvanometer to get the null deflection, and this is the manganese wire, and this is the for the battery we have taken the battery alternator which converts AC to DC. And first we'll see the circuit diagram and make the circuit diagram accordingly. So you see that first your galvanometer is connected to this middle point. So this is the point over here. So we'll take a long wire and connect the galvanometer first. Galvanometer is connected over here, and then this is connected to a pointer called as the jockey. This is the jockey pointer which is used to calculate the null deflection point. Yeah, the other part of the galvanometer is going to this particular point, middle point. So this is going to this middle point, and the manganese wire is connected in the left gap. So I'll connect manganese wire over here. We have to calculate the specific resistance of this manganese wire, and the resistance box is connected in the right gap. So over here. When you are making the connection, please check that the connection should be tight. Otherwise, it will create error in this reading. So I have connected the resistance in the right gap. This known resistance is connected in the right gap, and the battery should be connected across the two ends of the meter bridge. So use a long wire. This is the positive terminal of the battery supply that will be connected over here, and the negative terminal of the wire, this battery is connected to the other end of the meter bridge wire. So let's check the circuit diagram first. Battery is connected across the two end of the meter bridge, and galvanometer is connected over here in the middle, and then other part is connected to the jockey. And this is the unknown resistance, and this is the known resistance. So before you switch on the circuit, just check whether the circuit is close and tight. So now my circuit is complete, so I'll just switch on the battery. So please work on the low voltages so that there is low current and then there is no change in the length with respect to the large current. Now when you switch on the circuit, first touch it on the one end of the meter bridge. The galvanometer shows one-sided deflection, and when you touch it on the another end, the galvanometer should show in the other direction. So see over here, galvanometer is going in the opposite direction. This means that your meter bridge circuit is connected properly. Now, so first I have taken out 20 ohm resistance from this meter bridge, this resistance box. So I'll try to find out a position where the galvanometer is what? Null deflection or a zero. So see over here, the galvanometer is at this particular position, the galvanometer is the null deflection. So we have to note down this particular position. So this position, remember where the positive connection is connected. So this, from this only you have to calculate. So it is coming nearly 51 centimeter. So this length is called as the L, and this one is your the 100 minus L. So right now I am getting for the resistance taken out from the resistance box is 20 ohm, and the balancing length what I am getting is 51 centimeter, and over here it is 49 centimeter. So using this is for 51 over here and 49, you can calculate the resistance of the wire over here. So now what we can do is we can repeat the experiment. So let's say now I take out the 25, and once again we'll do the same thing. Check the two-sided deflection. See, it is going the deflection in both the sides. Now calculate what the null point. See, right now it is showing you the null deflection at, this is at 45. It is showing the null deflection at 45. So my reading will be over here. This will be the, I have taken out the reading over here, 25 ohm from the meter bridge, the resistance box. So over here this is 45, so it will be what? The 55. So this way you can take the different values over here, take the 6 readings over here, and let's say 30, 35 and 40. This way in the difference of 5 you take down the readings and calculate the balancing length in the L, and then the opposite will be 100 minus L, and we'll calculate what the known resistance. After taking out the 6 readings over here, take the mean of this unknown resistance. The next part of this experiment is to calculate the diameter of this wire, okay, using this micrometer screw gauge. So this is my micrometer screw gauge. First, I need to know the least count of this micrometer screw gauge. So we have over here the 2 scales for the micrometer screw gauge. So the scale over here that you can see is called as the linear scale or the main scale, and then this part is called as the circular scale. So how do we calculate the least count? Least count of the micrometer screw gauge is pitch divided by the total division on the circular scale. Now what is pitch is when I rotate this by one rotation, circular scale by one rotation, the linear distance travelled in the main scale is called as the pitch. So when I rotate once, then what happens is that the distance travelled in the linear scale is 0.1 centimeter. So, and the total division on the vernier scale over here is 100. So the least count is 0.1 divided by 100 is called as 0.001 centimeter. Now first we'll check any error present in the micrometer screw gauge. The positive error and the negative error can be there. So for calculating the error, then first we'll join these two jaws over here. When it just touches, then you see that the 0 of the main scale and 0 of the circular scale, if they coincide together, it means what? There is no error. Right now over here, the 0 is coinciding with the 95 of the circular scale. So from the 0 it is down 95. So there is this is called as the negative 0 error. So the 95 is from the 0, it is 5 into the least count is 0.001. So it is 0.005 centimeter. this reading is called as what? When the 0 of the main scale is coinciding the 95. This is 0 over here and this is 90 over here. So when there is downwards, it is 0 is coinciding to this downward value. This is called as negative 0 error. And this negative 0 error has to be always added into the reading to correct the reading. So first what we have to do is, we have to place this wire in between the two jaws when it just touches the wire, and then see the main scale reading. So main scale reading over here is 0 centimeter. So the main scale reading is 0 over here. And let's see the coinciding division right now. The coinciding division is, it is 21 centimeter. Sorry, 21. Coinciding division is 21. So least count will be the CSR will be, circular scale reading will be 21 into the least count. Least count is 0.001. So it is 0.021. So this is circular scale reading, and the total reading will be main scale reading plus this one, that will be 0.021 centimeter. So, and then this is a negative 0 error, so this has to be added over here. So this becomes 0.026 centimeter. So this is my correct diameter of this wire. So what you can do is, you can again take 2-3 readings over here at different position of the wire and repeat the experiment and take out the 3 readings and take the mean. That will be the diameter of your the magnetic wire. And then using the resistance what we have calculated earlier and this the diameter, you can calculate the specific resistance as rho equal to R A upon L. The R value what we have calculated from the previous experiment, and the area is pi into d square by 4, and the length of this magnetic wire we have chosen is 300 centimeter. So using this formula, okay, you can calculate the resistivity of this particular magnetic wire. So this is your main experiment. Yeah, thank you.